Okay, this video goes through emission spectra for dummies, as somebody called it. So what we're going to go through is working out basically how we calculate the wavelength of a light or a photon that is emitted when an electron that is jumped to a high energy level drops back down to a lower energy level, and in doing so emits a photon. Okay, so what we want to know about that photon is its wavelength. Okay, this requires some key information before we can start. So firstly, we need to know the energy level of the electron originally. So it jumps. It's going to start down at minus 5.45 times 10 to the minus 19 joules, and up here it was at minus 136 times 10 to the 19 joules. Now these numbers will always be given to you in an exam, so what we need to think about here is the key thing is that you've got an electron that's falling two energy levels in this case, and it's going from this energy level to this energy level here. So from this information we can calculate the energy that is emitted in the photon. So in this case, E is going to be equal to minus 1.36 times 10 to the minus 19 minus this number here. So that's minus 5.45 times 10 to the minus 19. So that number comes from there, and that number comes from there. Okay, so in this case, E is equal to, okay, so we need to calculate this now. So again, we're going to use our calculator on my trusty lunchbox. Hopefully you can see this display okay. So just watch what I do. Okay, so I'm going to go minus, start with a bracket, minus 1.36 times, and then we put another bracket, 10 to the power of minus 19, and then we tab forwards and we close that bracket twice, because obviously this bracket and this bracket match up, and that bracket matches up with the bracket at the end. And then we're going to minus, put another bracket, we're just starting another sum, minus 5.45 times bracket 10 to the power of minus 19, close the bracket, and we go equals, and we end up with this number here. So we end up with 4.09 times 10 to the minus 19 joules. Okay, so there's our energy. That's the energy contained within that photon. We'll put that calculator to one side because we don't need it at the moment. What we now need to do is we need to use a formula. So the formula that we're given on the formula sheet is this one. So this is that the energy is equal to Planck's constant multiplied by the frequency. Now we know the energy because it's here. We will also know Planck's constant because we're given it in an exam situation. So it's 6.63 times 10 to the power of minus 34. And the frequency is our question mark. So what this means is we need to rearrange this formula to make F the subject. Okay, so F in this case is equal to the energy of the photon divided by Planck's constant. So the energy is going to come from here, and Planck's constant is going to come from here. So the frequency is going to be equal to 4.09 times 10 to the minus 19 divided by this number, 6.63 times 10 to the minus 34. Okay, so what is that number? And we need our trusty calculator, and we need to be comfortable with using these all the time. Okay, so we're going to do brackets 4.09 times bracket 10 to the power of minus 19, close that bracket twice, divided by bracket 6.63, didn't quite hit the point there, 6.63 times 10 to the power of minus 34, shut that bracket twice, and we get that number there. So this is 6.17 times 10 to the power of 14 hertz. So that's the frequency, and I've rounded that to 2 decimal places. You can keep that number as a whole if you want. It's really up to you. That should give you the answer, close enough to the answer that we need to do. Now at this point we know F, and what we're going to do is we're going to work on the basis that this is the speed of light, because it's a light wave, and we know that for the sake of simplicity we're going to use this as 3.0 times 10 to the power of 8. This should be given to you in the exam, meters per second. Okay, what we're then going to do is we're going to use this formula, V equals F lambda. Now we know V because V is here, plug that into there. We know F, plug that into there, but we don't know the wavelength. So in this case, wavelength is equal to velocity divided by frequency. That is therefore going to be equal to 3 times 10 to the power of 8 divided by this number here, so 6.17 times 10 to the 14, and then that gives us, again we're going to need our calculator at this point, so we go 3 times 10 to the power of 8 divided by 6.17 times 10 to the power of 14, close the bracket, and we get, again we use our S to D number here, and it gives us that number there. So this is 0.10 0.0033486 meters. Okay, what we're going to do is going to change my color pen because I'm drawing over this arrow. This is in meters and we want it in nanometers. Okay, so meters to nanometers, we need to times by 1 billion. So that's 1 with 9 zeros on the end. Okay, so sorry I've had to do that like that, but you should be able to make that out. So it's multiplied by 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and it gives us 486 nanometers, which we've worked out to be blue light. Okay, so that's emission spectra for dummies, as you called it. Hopefully there's no questions from that. If there are, please do let me know. Again, there are a couple more example questions on the website that you can go through, and I'll go through those as and when I get chance over the next couple of weeks. Okay, so hopefully